Hello students, welcome to Saraswat classes, and this is Dr. Sarkar over here. We were discussing the synthesis pathways of aldehydes and ketones under the topic of retrosynthesis, and herein in the section B of the lecture we are going to discuss the synthesis of aldehydes, ketones via acyl substitutions, in which first of all we will discuss synthesis of ketones via organometallic reagents. So out here one might say that the reaction of an organometallic reagent such as Grignard reagent, which is abbreviated as R prime MgX, with a carboxylic derivative such as an ester RCOR. Now usually reaction with this reagent leads to addition of two equivalents of RMGX to ester to give tertiary alcohol as the product. But there can be conditions produced in which we have kept the ester in excess in a highly diluted solution, and we are using RMGX. So idea is to add RMGX to the solution of ester so that ester always remains in excess and RMGX remains small amount. So essentially by this method we have produced a condition in which we can think one equivalent of the RMGX is going to react always with the ester, and if we follow this reaction with the acidic workup, then we will see that ketone is the major product out here. So this is one way of producing ketone from a ester using Grignard reagent, which is RMGX. The other procedures that one may use involves the reaction of an acid chloride or any halide with an organocuprate, or the reaction of Grignard with the alkyl nitrile, followed by hydrolysis of the imine product of the resulting imine product to give ketone. The above discussion can be represented as follows. We have the acid chloride, and one may use R2 CuLi in THF, followed by acidic workup to give the desired ketone, or one may use the nitrile, alkyl nitrile, in which Grignard reagent RmGbr followed by the acidic workup gives us the desired ketone, in which on adding Grignard we are getting a imine product which is our intermediate, and this on acidic workup via hydrolysis will give us the ketone product. One may also use organocadmium to achieve this synthesis, in which one can use R2CD in THF followed by the acidic workup, and that also will give us our desired ketone. Okay, so these can be used. In the next part we are going to discuss the synthesis of aromatic ketones, and here we are involving the name reaction Friedel-Crafts acylation. So in the Friedel-Crafts acylation, the reaction of an aromatic compound with an acid chloride takes place. Let the aromatic compound be benzene and let the acid chloride be RCOCl. In presence of a Lewis acid, which is the anhydrous AlCl3, out here a acyl group that is produced via the reaction of the acid chloride with AlCl3 okay, this produces the acylium ion, which is stable because it is resonance stabilized. Okay, this is our electrophile, and so out here after the acidic workup the desired aromatic ketone is formed over here. So basically the RCO undergoes aromatic electrophilic substitution reaction. So this is our CrOH. Now that then loses the proton, but O having the oxygen will form the adduct with the excess amount of aluminum chloride that might be present, which can be removed by the acidic workup to give us the desired aromatic ketone. The electrophile does not undergo any rearrangement. The reason we have already mentioned, because it is resonance stabilized. So this is basically the reaction scheme for Friedel-Crafts acylation reaction. Now, if we were to synthesize aromatic aldehydes, in that case, one can do it from toluene to benzaldehyde using the Gattermann reaction. That is one of the procedures. One may also involve the CHCl2 group, which on base reaction with the base, okay, that is NaOH aqueous, will give you the benzaldehyde. The reagent for Gattermann reaction obviously is chromyl chloride, which is CrO2Cl2 and followed up O2Cl2 in acetic anhydride, and which is worked up with the acid to give us the benzaldehyde. So these are two procedures. Other procedures can be formylation, reaction, okay, but formyl chloride is unstable and too reactive. So there are 2 to 3 synthetic pathways by which this reaction can be done. So suppose if one thought of reacting the benzene, okay, with something that will give us this, A and B won't be used over here. We have to think of something else. So if one thought that we can use HCOCl, but HCOCl is highly reactive and cannot be used in presence of AlCl3. So we need some other synthetic equivalent for this. One pathway is to use the Gattermann Koch synthesis. So this will give us one of the formylation procedures in which the benzene is treated with, or any alkyl benzene is treated with, carbon monoxide in the presence of HCl and AlCl3, wherein carbon monoxide and CO combine to produce the formyl chloride in C2, which is as follows. So we have the C triple bond O, this is your minus and that is your plus, that is your HCl. This is going to combine like this to give you HC triple bond O. Alright, this will be attacked by Cl to give you the production of HCOCl in the reaction conditions. Now once this is formed, what one can think is that the HCOCl in the presence of AlCl3, okay, will give you the desired benzaldehyde. Okay, so let's write it over here. Okay, so we are trying to say that these reagents eventually produce this, okay, and which is now being used to form this product. Okay, so this is basically again very similar to Friedel-Crafts acylation. Okay, so basically we are producing the benzaldehyde over here. Another process is using the Vilsmeier Haack procedure or reaction, and in which the reagent NN dimethyl formamide, that is your DMF, is the source of the formyl group. So basically there is a reaction between the DMF and phosphorus oxychloride, that is POCl3, which will lead to the formation of formyl chloride synthetic equivalent, which is this. That means eventually this one. Now regarding the mechanism, I am drawing it out here. So over here basically, suppose one thing more, that this reaction is favorable only for highly electron rich systems. So if we are using a phenol out here, the reaction will take place to the electrophilic center, that is the carbon. Okay, the system should be a activated electron rich ring I mean benzene ring. So this will eventually lead to the formation of this product using aromatic electrophilic substitution reaction. And finally, hydrolysis of the imine will give us our desired product, that is para-hydroxybenzaldehyde. I hope we have discussed or covered all the synthetic procedures that can be discussed regarding aromatic aldehyde and ketone preparations. In the next lecture, we will take up further synthetic procedures. Keep visiting Saraswati classes, and thanks for listening. This is Dr. Sarkar saying goodbye. Have a great day. Stay well.